Linear Algebra for Flow Regulation by Jonathan Mondragon and Yash Rupawat. A system of linear equations is a collection of linear functions, each of which graphically represents a straight line. Linear algebra is central to many areas in mathematics, sciences, and engineering because it allows the modeling of natural phenomena and efficiently computing with these models. An important industrial application of linear algebra is analysis of flow regulation. It involves modeling of problems involving flow through a network system. For example, analysis of traffic flowing through a network of streets, or solving for current flowing through a circuit. Also, we can solve complex chemical equations with the help of linear algebra. Traffic flow regulation. This application of linear algebra involves modeling and predicting the flow of traffic through a network of streets. Let me demonstrate this application with a simple example. The following is a schematic diagram of traffic flow in the network of streets. For simplicity purposes, we use a system where the traffic flow is one-dimensional. These values represent the number of vehicles entering the system per hour. These values represent the number of vehicles leaving the system per hour. These variables represent the traffic flow on each of the roads inside the system. The values of the number of vehicles entering and leaving the system are measured by the Department of Transportation. The flow of traffic inside the system is dynamic and constantly changing. Hence, it is analyzed by the engineers using concepts of linear algebra. Based on the data, we model linear equations at each intersection. For each intersection, the number of vehicles entering the intersection is equal to the number of vehicles leaving that intersection. We then simplify the linear equations in a form that can be modeled into an augmented matrix. This is the augmented matrix for our system of linear equations. Note that since the number of variables is more than the number of equations, our system has infinitely many solutions. We then perform the Gauss-Jordan elimination on the matrix to transform it into the reduced row echelon form. The circled values represent the pivot entries of the matrix. A pivot entry is the first non-zero entry in each row when the matrix is in the row echelon form. As you can see, column 3 and column 6 has no pivot entries. These result in free variables, which is another indication that our system has infinitely many solutions. From the previous matrix, we obtain the following parametric solutions. x3 and x6 are free variables as there was no pivot entry in column 3 and column 6. These variables can assume any values as long as they are valid. The remaining 4 variables depend upon the values of x3 and x6. These vectors represent the solution of the system of linear equations, where P represents the particular solution and V of h represents the homogeneous solution. V of h assumes values depending upon the values assumed by x3 and x6. Looking at the equation, we know that x3 has to be greater than 40 for the data to hold true. Here, we were successful in modeling the traffic flow in a network of streets. We were successful in determining the roads which were more important and which were more traveled in the system. Here, we saw a very basic example of a real-life application of the concepts of linear algebra. Engineers in the transportation department apply similar concepts to more complex road systems to analyze and regulate traffic flow. The analyzed data equips the transportation department to deploy better electronic and visual signals, ensuring smooth flow of traffic.